for the latest talk. We have Yashwant Gandhi from Silence Laboratories.
Hi, yeah, thanks for the introduction. So I'll be speaking about MPC for private compliance checks, which is joint work with Nilesh Premradka, Daniel Noble, and Sriram Sridhar. So actually, Daniel was supposed to give this talk, but he wasn't able to make it in person, so I'm presenting his slides on his behalf. Okay, so the background for this talk is Project Mandala by the Bank for International Settlements, which is a project that's run in collaboration with a number of central banks, specifically those in Australia, South Korea, Malaysia, and Singapore. And the problem statement itself was formulated after a bunch of extensive consultations within the industry. And our role in this was to design the MPC protocol that fits as part of a larger workflow and to implement and provide the solution. Okay, so taking it for granted that cross-border transactions are a cornerstone of the global economy, the freedom to move money across borders also does come with some restrictions in terms of maintaining compliance with anti-money laundering regulations and like checks that make sure that you're not committing financial crimes and so forth. So a lot of these compliance checks that that make sure that you're compliant with whatever anti-money laundering, whatever financial crime regulations, at the moment are centralized. They are conducted in many cases manually, which makes them quite slow and also expensive. And the companies that conduct these checks are quite opaque in the way they operate. And unfortunately, they also throw up a lot of false positives. And if you happen to have a transaction that's falsely flagged as not being in compliance with whatever mechanism, then it's a very tedious manual process to go in person, do some KYC, something like this, and get things corrected. So the solution that BIS identified, or that BIS wants to try out, is to use MPC to automate these checks. In particular, the idea is to have banks validate with each other in a peer-to-peer fashion that whatever transaction is being proposed is compliant with the relevant regulations. And yeah, now, because these checks involve some private data on both entities' sides, we need to use something like MPC to make sure that we're able to get the functionality of the checks while also keeping the relevant data private. Okay, so what are the checks exactly? The first check is that of a private sanctions list. I mean, the check that the entities involved in the transaction don't appear on any sanctions lists. So it proceeds as follows. There's an originating bank that has a proposed transaction, which has to be verified with a sanctions list that's held by a beneficiary bank. So part of the sanctions list is public, so that check, the first half is straightforward. Part of the sanctions list that's held by the beneficiary bank is private, and so we need to run some sort of secure protocol for the originating bank to confirm that the entities involved don't appear on the sanctions list, on the private sanctions list. And this is quite straightforward, at least from a protocol design point of view, because this is an immediate application of private set intersection. And the protocol that we use is very similar to this one by Yereke et al. From a few years ago. The more interesting one, at least for an MPC audience, is capital flow management, because there are a lot of jurisdictions in which the amounts of certain capital flows are restricted. I mean, there are like daily caps and so on. So for example, Malaysia, which is one of the countries involved in this trial, has this regulation that companies hold no more than about 100 million Malaysian ringgits in debt, which is about 22 million US dollars. So in this case, the test that has to be done, or like the predicate that has to be evaluated before approving the transaction, is more complicated, because now we have to check that the total sum of capital flows doesn't exceed a certain threshold. And specifically, we want to check if were this transaction to be executed, will the result be more than a certain threshold? So yeah, this is roughly the architecture. The originating bank, once more, has a proposed transaction, and it wishes to confirm with the central bank, which has the list of all prior capital flows for a number of registered entities, that executing this transaction won't cause the total sum of capital flows for this particular recipient to exceed the limit L. To say a bit more about the setting, what we want now is a two-party protocol. So this is in the dishonest majority setting. We want malicious security. We want to make sure that nothing goes wrong if either of the parties were to deviate from the protocol. And the operation that we have to implement specifically is that of selecting like obliviously from a list of aggregate capital flows, and then performing a couple of operations that have sort of conflicting native representations, addition and comparison. In a little more detail, this is the ideal functionality. So there's an originating bank that has as input a transaction amount X, which is an integer, and an identifier for the entity involved, that's Y. On the other side, we have a central bank CB that has a list of identifier and total sum pairs. So each of these parties privately provides their input to the functionality, and the functionality proceeds in two stages. The first stage is to match the identifier provided by OB with a certain element in CB's list. And the second stage is to read the integer that's in that particular location of the list and perform a sum, like check if X plus Z sub I, where Z comes from the second list, is less than a public limit L. If so, set the output to be 1, otherwise set the output to be 0, and return the output bit to both parties. Of course, this is a two-party functionality, so you can think of outputs being adversarially delayed. Right, so that's the ideal functionality, and the protocol that implements it sort of naturally follows this two-stage structure. The first stage is to obtain an authenticated secret sharing of the obliviously read element. Right? So if Z sub I, which is the ith element of the list, the one that's relevant for the transaction, is obliviously read, this is how it proceeds. Okay, so the first step, okay, it's not that clean. Okay, so the first step is to have the central bank, that's the one with the list, to sample a statistically large one-time pad ZCB, and for later on, it's also going to sample some MAC keys. And the second step has the central bank using these one-time things. So remember, there's only one pair of MAC keys, and there's only one statistical one-time pad. It uses the one-time pad to encrypt every element individually in its list. And it uses the MAC key to also authenticate, it applies the MAC key to compute a MAC on every element in the list. And note that these are actually one-time values. So ZCB and AB, these are individual one-time use values, but we are reusing them across every element in the list. We're using the same one-time pad to encrypt every element. We're using the same MAC keys to authenticate every element. Why is this OK? Because the next step is an augmented PSI functionality. So think about PSI plus transfer as being a private set intersection where, in addition to just checking a match, you can also transfer some data that's associated with the matched element. This is quite straightforward if you think about how PSI protocols usually work, because usually these protocols follow some structure where there's an OPRF that's, there is a list of PRF values that's computed on one side, and then the other side, the other party evaluates the same PRF obliviously. So you can use that common PRF value as an encryption key, basically. It's quite straightforward. It's a simple modification of the PSI functionality. Right, so on the one side, the OB entity inputs its index that it wants to read, or it inputs the name of the entity that is relevant to the transaction. On the other side, the central bank puts in the list, this like padded list that it just computed along with the accompanying max. And finally, the output here, because OB is able to read basically just one entry out of this list, that is one padded value and one MAC'd value. The fact that the same pad and the same MAC are like reused across a bunch of terms, like that doesn't matter, because it serves its role as a one-time pad. Okay, now to explain a bit about why did I use a statistical one-time pad here instead of a perfect one? It's because the next stage is the actual comparison part, like testing if the threshold has been exceeded. And rather than computing this predicate naively, so assume that I have a two-party computation oracle now, right? Rather than computing this predicate naively, I compute a slightly more 2PC-friendly predicate, and again, explain why in a minute. So basically, the left-hand side, the predicate that we actually use the 2PC to test is X plus ZOB is less than L plus ZCB. And basically, if you just like rearrange the terms, you just get back this thing. Why did I do this? Because now the entire left-hand side is known to OB, and the entire right-hand side is known to CB. So this is going to make things a bit simpler in a minute. Right, so basically the 2PC just tests this predicate, and the MAC value that goes along by the side is like a standard information theoretic MAC that makes sure that the output of stage 1 is correctly input into stage 2. Right, so what does the 2PC do? It does a couple of things. It runs the comparison and also makes sure that it's using the correct output from stage 1.
Yash, what if the thing overflows?
Yeah, so this is an integer secret sharing, right? I mean, this is why I use the statistical one-time pad. So the authenticated secret sharing over here is an integer secret sharing. So that preserves the integrity of this check. Yeah, I should have made that explicit. Yeah, okay, so what 2PC to use, right? Yeah, I mean, there are ways, given that we have to handle two different kinds of computation, as in additions and map verification are natively arithmetic, and comparisons are best expressed as Boolean circuits. It's not immediately obvious what protocol would be the best over here. Like, I mean, the criteria that I would like for a protocol here is not necessarily like the most efficient state-of-the-art thing that does like 50 different optimizations. It's more just a protocol that's simple, easy to describe, and easy to implement. And at the moment, at least for this phase of the project, this is something of a trial. So like, the best possible efficiency is really not on the table. It's just we want something that runs in reasonable time. So what we opted to do is to use an arithmetic-based 2PC. So you can think of Bedoza, in which each of the shares are mapped individually. And we compute basically authenticated Beaver triples using oblivious transfer-based vector oblivious linear evaluation, like OT-based WOL. We basically repurposed this WOL that we had from a threshold ECDSA signing library. Right, so recall that I mentioned it's important that the left-hand side, the fact that the entire left-hand side is known to OB and the entire right-hand side is known to CB makes things a bit easier. This is because, we don't have, because the comparison part is kind of a Boolean circuit, as in the comparison part is a Boolean circuit, it needs bits as input. It works most efficiently with bits as input. Rather than doing this like arithmetic to Boolean conversion and so on inside of the 2PC, we can just use the fact that each side of the inequality is known to one party, so you can directly input a bit decomposition. And yeah, I'm hand-waving a bunch of details, which is that you need to verify that all these inputs have been put in correctly and so on. You need to verify that the inputs are effectively all positive. And also, another kind of real-world caveat, I would say, is that we were told for this phase of the project, input validation is not really within scope. So it's not the case that these lists, for example, have to come from any like externally audited source or anything. So what that means is effectively the ideal functionality itself permits selective failure. So it's inherent that there's always going to be some entries in the list that are malformed or something like this. This is something that's possible in the ideal protocol itself. But what we have to be careful about is that the protocol doesn't induce new avenues for selective failure that are not already in the ideal functionality. Right? So we need to be able to map every protocol behavior to some perhaps malformed entries in the list in the ideal protocol. So what that means is that we have to be careful about where the aborts happen. So we have to make sure that, for example, there are there are places in the protocol where OB observes that CB is cheating, but aborting over here would reveal something that it doesn't want to leak. And so we have to withhold all aborts until the last stage of the thing. Yeah, so a few caveats over there. I mean, a few things to keep in mind. All right, so that was an overview of the protocol. It's not super optimized either in terms of design or implementation. Roughly, the thing that I want to say is that it takes on the order of a minute to like a couple of minutes, minute and a half to run the computation from end to end. On like fairly standard hardware, I think there's a lot of scope to optimize the implementation, also in terms of protocol improvements. And also maybe we can explore things like the offline-online paradigm to speed up the like online comparison time and so on, or like the online time. Right, so this is currently, the library that we built is currently being tested in a pilot study by these national banks, by these central banks. There are like I think the Australian bank and the Korean bank has some specific use case, and the Malaysian bank and the Singaporean bank have some specific case for which they're using these checks. Yeah, so cross-border transactions are a particular application for MPC, which seem to make sense because at the moment it's a sort of slow centralized process. And at the moment it's run by these like opaque trusted entities, which come with some problems. And MPC basically facilitates this compliance by design kind of approach as identified by BIS. And it allows banks to unlock some private data that was otherwise restricted by regulations and so on, to execute these checks to sort of cut out the middleman. And there are two checks actually. There's the private sanctions list one, and then there's the capital flow management check. But I presented the capital flow management one in more detail because I figured it would be more interesting to an MPC audience, because it does involve some non-trivial MPC operations. So the technical white paper that has the protocol in full detail is online at the first link. That's not a very wieldy link, but it's a clickable thing in the PDF if you're interested afterwards. And the overall project report by BIS is at the second link. And yeah, I'm happy to take questions.
Super. Let's thank. Questions. Lovely.
Very nice talk. This capital flow management protocol that you come up with, you mentioned that it has to be actively secure. Why? Like, what's the surrounding conditions that made you settle on that choice?
That wasn't so much a choice on our part as much as it was maybe like discussing with the BIS people. It seemed that they were keen on getting active security, as in if something. I'm not sure like if this maps to any specific regulation or anything. That's probably a good question to have.
Because it seems like if you introduce like active security, and the task here is to figure out if some transaction overflows a limit, like an easy way to do that is just lie about the amount being transacted, right?
That's true. So this is okay. So I should mention a couple of things. One, that's true. This is not at the moment within scope because input validation is not within scope. And another is that this is not the final check. So this is sort of like a pre-validation kind of thing. So this sits somewhere earlier on in the workflow. If you happen to lie about something and the transaction actually does cause problems later on, then that you'll be in more, like, as I understand it, you're more incentivized to be honest about your inputs at this point.
More questions, and Brian starts to prepare for his session. Yes. Abi.
1 minute
Oh.
for the workflow?
Yeah, compare this against like taking a day to resolve some like false positive or something. But yeah, there's going to be a second phase for this project pretty soon in like a couple of months. And conservatively, I estimate that we can get this down to less than a second. At the moment, like nobody's complained. So we were told specifically that like efficiency is not a priority over here. Again, maybe we were told that by people who didn't have MPC backgrounds, let's say. So like not be careful what you allow for inefficiencies in MPC, I guess, is a lesson here. But yeah.
This is perhaps a stupid question, but what's the expected number of transactions in the real world that you expect to have once you deploy this thing?
Oh, yeah, that's a good question. I'm not really sure because at the moment this is just like a limited pilot. I'm not sure what the volume of transactions here is at the end. I think it's going to be like a pilot phase for a little while.
Very cool. Brian, I think you're up. Let's thank the speaker just once more.